I'm starting.
Okay.
Yep.
So, hi everybody. So, welcome to the 21st talk in this Tunneling in QFT series. Today, we're very happy to have Javier Subils presenting his very interesting work on microscopic description of critical bubbles using holographic methods to do very interesting stuff studying these bubbles. So Javier has completed his PhD in 2021 in Barcelona with David Mateos. He's been a postdoc in Nordita and now in Utrecht University. And yes, he's done a lot of very interesting work with these holographic methods. And yeah, we're very excited to see what you have to say. So please take it away.
Yeah, thank you for this very nice introduction and the invitation. Yeah, so what I will discuss today is this project that we put, well, early this year in the archive together with Carlos, David, and Vilke. I suspect, well, at least I saw David, but maybe also Carlos and Vilke are in the audience. I don't see them. Um, and yeah, so we are probably very much aware that our physical phenomena is full of phase transitions. These are rather ubiquitous phenomena. Also in our daily lives, when we boil water, for example, or we stare at melting ice. But if we are here, it is probably because we are also convinced that these phase transitions play or may play a crucial role in more fundamental phenomena, such as in cosmology or astrophysics. So it is proposed that the first order phase transition in the early universe could lead to a detectable gravitational wave signal. But we know at the same time that the standard model, in the standard model, is no first order phase transition. Neither the QCD phase transition nor the electroweak are first order. So in principle, this would not lead to a detectable gravitational wave. The reason why is because when you don't have a phase transition, you don't generate these phases of well, preferred phase in the phase transition. You don't generate these bubbles, which are precisely the characters that, when they expand and collide, generate this microwave gravitational stochastic background. So in a way, you could say that this is bad news, at least for a standard model. But if you're a little bit more optimistic, that's actually good news because it would mean that such a detection would imply directly detection of new physics. So that's exciting. A similar situation where these phase transitions may play an important role is in astrophysics when you look at neutron stars, because it is proposed that the QCD phase diagram has also some sort of first order phase transition at high densities and low temperatures. And that's precisely the relevant region for neutron stars phenomenology. So also in this context, detecting such a phase transition would lead to something that it has been already proposed for years, but it's very difficult to access experimentally, which is whether QCD has or not this phase diagram. And actually, this is something you may see during mergers. So there's been already some simulations of neutron star mergers when people have observed that the matter, when it's been compressed and heated up during the merger, well, this is of course a model-dependent statement, but in certain models you see that the matter wants to transition to a new phase, and this actually could lead to a detectable characteristic emission of gravitational waves in the megahertz band. This is something that was proposed by David and collaborators. Okay, this is also depends a little bit in the parameters of the model, but tell us that it is very important to understand what is the physics of this first order phase transition, both in cosmology and astrophysics, so that we can precisely determine what is the expected signal and yeah, the concrete characteristic we expect to observe so that we can pinpoint what's the phenomena that's behind this detection, if ever detected. Okay, so that's the motivation. And in this talk, I will focus in the question on how do these bubbles nucleate. So of course, there's very complicated phenomena here that involves the nucleation of the bubbles, but also the expansion and collision of the bubbles and the walls. And in this talk, I will only focus in the nucleation part. And then I should say that it's very good if you stop me, either if you don't agree with anything I say or if there's any question, because I tend to rush if I don't get questions. So it's very good that you interrupt. So just unmute yourself and do that. Okay. Good. So the plan for the talk is, well, maybe review something that probably most of you are very familiar with, which is how we deal with this bubble nucleation in an effective field theory approach. Then I will present our microscopic description and the results we got. And after that, I will get back to this effective description so that we can compare them. And actually, I will claim that our microscopic description provides a way to assess the validity of this effective description. And well, then I will conclude and present possible follow-ups of this framework or project that we propose. Good. So when you want to understand phase transitions, well, maybe the object you would pay attention to is the partition function from theory, because it informs you about the free energy of different states by evaluating the Euclidean on-shell action of the theory. Well, this may be a very complicated object to evaluate because, you could have many fields, it can be strongly coupled, it can have complicated physics. So in many situations, you rely on the existence or on your capability of constructing or focusing your attention in an effective action that you hope it captures all the physics in some simpler terms. So for example, here I'm having in mind the effective action you would get for the electroweak theory when you only keep the vacuum expectation value of the Higgs as your order parameter and you have kind of integrated out the rest of the physics. And then, okay, if you tune, for example, in the electroweak theory, your parameters properly, well, you can get this kind of standard phenomenology for your effective potential that describes phase transitions. Let me explain or review why. Well, this has, as you see, minima and also a maximum. So the claim is that this minimum would correspond to equilibrium state, homogeneous equilibrium states of your system. Why is that? Well, because when you have a homogeneous state, you don't have the derivatives in phi. So when you evaluate the value of the effective potential, it's directly giving you the free energy. That means that the lowest minima corresponds to a stable phase, and then the highest minima is metastable in the sense that, well, the system would like to fall into this other minima, but there's a barrier between them. A way I like to plot this is in terms of the free energy, which contains the same information, but now I'm plotting kind of the value at the extrema as a function of the temperature. And then we see very clearly these three branches of the stable phase corresponding to the lowest minimum, the metastable, which is the other minimum, in this case sitting at 0, and then the unstable phase, which I will also refer to as the spinodal branch, which corresponds to the maximum. And similarly, well, now once you have the free energy, the temperature, you can get other thermodynamic quantities, such as the energy as a function of the temperature, which shows this peculiar and characteristic S-shape of first-order phase transitions. And then again, if you imagine that this describes some state of the universe that is cooling down because it expands, well, at some point it hits the critical temperature at which these two branches cross, and the system wants to fall into the stable phase. Now, the question is, how do we describe this falling or this transition? Well, something very simplistic you could say is that, well, as soon as the system is here, you can actually start generating chunks of the new phase. So that would be what's sometimes referred to as the Maxwell construction. You don't, well, you say that this is kind of automatic. There's nothing suppressing the nucleation of the new phase. So, okay, you just follow this vertical line in which you are reducing the energy and generating a phase-separated system with two different phases. Now, on the opposite limit, you could say, no, this is always suppressed, like falling from this branch to this other branch. So in that case, you would follow all these branches up to the spinodal point where the branch disappears. And then here, well, you would imagine that very violently your system goes out of equilibrium and eventually it will relax back in this other branch. So, okay, I'm kind of crossing it, but you don't explore this branch because you're just here and want to relax somewhere here again. So these are kind of the two extreme approximations you could take, but generically what would happen is that somewhere in the middle, you would start nucleating bubbles of the new phase. And that's the thing I want to discuss, right? So how can we explain this nucleation and, well, give a rate for it in a way. And in this context, a main character to describe this, this process is the critical bubble. So the critical bubble is a bubble of the stable phase surrounded by the metastable phase, which is in the threshold between expanding and contracting. So the idea is that if at some temperature you get a bubble which is smaller than the critical one, it will shrink back. If it's larger, it will start expanding. So the critical one is the one that is static, but in a way it's unstable. As soon as you touch it, it will either expand or contract. And this one is the one that sets the probability of the nucleation itself, because it's the easiest to nucleate. More precisely, what you would compute is the on-shell action corresponding to the bubble, and you would compare that to the, on-shell action that I was saying here of the metastable phase that you have outside. And in a way, this is giving you the probability of generating this bubble. Or put it differently, the difference in the free energy between the bubble and the homogeneous phase will give you the suppression in this probability, or the suppression of this process of the bubble. So, now the question is, how do we compute this? Well, there's one limit in which you could think that the bubble is sufficiently big so that you can approximate the wall of the bubble by something very thin. And in that case, you could think that delta F is just given by some surface contribution. And here I'm putting the surface tension sigma, that will be important later, plus a volume term. So here you would have, indeed, right, sigma times the area of the bubble plus the difference in free energy densities times the volume. And because the free energy density is minus the pressure, you could also write it this way. And if you extremize this, you would get precisely the radius of the bubble, which goes as 1 over delta P. Now, remember, delta P is 0 at the critical temperature. This means that you expect this approximation to be valid close to the critical temperature. And then if you reinstate this back in this equation, you will get this very interesting equation that we will discuss later, which tells you what's precisely this suppression in terms of sigma and the difference in pressures. Good, so this is the standard story, and then, this is only in this limit. If you wanted to compute, bubbles in which this approximation does not apply, but you want to compute them from the effective action, you could find equations of motion, the equation of motion of this action, compute them, and then evaluate the action. You have to do this numerically, and then you would get the nucleation at different temperatures. Right, so that's the effective approach. And now I will present the holographic approach. So the idea is that here, to construct this effective action, you are in a way ignoring part of the microscopic features of your theory, just because you are maybe integrating them out or, keeping this only second order in derivatives. So now the question is there any way to get, the full microscopic tunneling rate, for example, that does not ignore any of the physics? And that's something that you can do in holography. So let me briefly present this holographic approach. For the purposes of this talk, holography will be a duality between some gravitational theory in 5 dimensions with a negative cosmological constant and some gauge theory in 4 dimensions, in flat space. And you can really think this as a duality, as a map that matches observables in one side to observables in the other one. Both sides have a characteristic or important, actually 2, dimensionless parameters. In the gravity side, what matters is how the scale set by the cosmological constant compares to the Planck scale and the string scale. This is meaningful because, it arises in the context of string theory. And these are related to the rank of the group. So, this is a non-abelian group. We'll have some SUN group if you want. And here that n is precisely the rank of that group. And the other meaningful parameter is what's typically known as the Toft coupling, which is a combination of the coupling of this Yang-Mills group and n. And then the way these are related, it's really that, the first of these parameters scales is related to n, while the second one is related to lambda. And that's why this is actually quite interesting, because you are supposed to trust the gravitational description when lambda is large, because in that case, string corrections are suppressed. And similarly, when n is large, so that quantum corrections are suppressed. So the gravity side of this duality is giving us access to the strongly coupled regime of the gauge theory. And it's not necessary, but extremely convenient sometimes to think of this gauge theory as living at the boundary of this space-time. So this is a four-dimensional gauge theory. You can think that it's living at the boundary of this space-time, which I will typically represent in this way. Is there any question so far?
I do have actually one question.
Yes.
There's this negative cosmological constant. What does that map onto in the quantum field theory?
Right. So, the cosmological constant is really giving you this L. Right. So it's mapping to N.
Okay. So
So
dimensionless quantities that map onto and yeah.
Exactly. It's dimensionless quantities that you relate in both sides. So I guess that's the shortest, cleanest answer to what you're asking. But I'm not thinking of this gauge theory as living in a negatively curved space-time. So this will live in flat space. So that will help me to get all the thermodynamic quantities I'm interested in, for instance. It's just the way these two sides are related. Yeah, thanks for the question.
Thanks.
Good. Okay. So now that I told you, there's a lot of background in this, but I told you there's this duality. It's good to know, and kind of people build a dictionary to relate quantities in both sides of the duality. So, for example, and that's kind of what's going to be relevant for us, black hole geometries in the gravity side will be related to different phases in the gauge theory side. And the geometric properties of these black holes will be giving us access to the thermodynamic quantities of the different states that I will consider. For instance, the area is related to the entropy, the usual way, the mass to the density, and the surface gravity to temperature. And it's also good for the intuition to think of small black holes, meaning black holes whose horizon is far from the boundary, as describing low energy phases, and large black holes whose horizon is close to the boundary, as describing high energy phases. Now, kind of the cool thing of holography is that it's not only giving us access to the equilibrium phases and equilibrium properties, it's also giving us access to near equilibrium properties. So if I consider perturbation of this metric, if you wish, gravitational waves in the five-dimensional metric, this encodes transport properties such as viscosities in the gauge theory side. And more importantly, I can also consider non-trivial configurations of this horizon that could be either static or also evolving in time, and that those would map to non-trivial configurations of the quantum fields in my gauge theory side. That's something which is very complicated to have access to with other techniques, say maybe the lattice, or that's the one I have in mind. But holography gives you, a precise map between the energy momentum tensor of such configuration and these geometries. There's some computation you do close to the boundary, and what I'm trying to stress is that this is a precise and provides information of the quantum or expectation value of the quantum energy momentum tensor without any approximation taken, any effective approximation rather than the ones I already said, that n has to be large and lambda has to be large. So in that sense, I'm saying that whatever this side of the duality gives me is a microscopic description. It's giving me access to the full energy momentum tensor of the theory. So let's exploit that. Now, if you just take the ingredients I wrote, which was gravity and a cosmological constant, the theory is too boring. It describes a CFT, and it doesn't have any phase transition. So I need to modify a little bit and put more ingredients to get phase transitions, which is what I'm ultimately interested in. And for that, it's enough to consider a scalar field, which is an appropriate potential. Now, this potential is the potential of the scalar field in the bulk, in this geometry. Has nothing to do, well, it's related, but it's not the potential that I would get in the effective theory, right? Even though for both of them, I will use V. They are actually related, but in an intricate way. So here I just choose some potential that will give me the phase transitions I will need, as I will show you. And the dictionary states that by reading off what the field is doing in the different solutions close to the boundary, I have access to the source of the field. So in the gauge theory side, I'm deforming my original gauge field by some operator with a source. So the leading coefficient close to the boundary is giving me the source of this operator, while the subleading is giving me the vacuum expectation value of the operator that I'm introducing, which I will identify as my order parameter. Good. So that's the map, and now we will use it. As I tell you, if now I start constructing black hole solutions and considering solutions whose horizon keeps going down and down into the bulk, I'm exploring the phase diagram. For instance, I'm plotting here the energy as a function of temperature. And again, with a convenient choice of this potential, I discover that there are indeed these phase transitions. So I start decreasing the energy of these configurations. Eventually, there's a phase transition. I'm not showing it, but here the free energies also cross themselves. And I have exactly the same phenomenology I was discussing at the beginning, this characteristic S shape, where I have the stable phases, then some metastable phases, and an unstable spinodal region in between. Good. So that's kind of what I needed to expect these critical bubble solutions to exist. So let's see. Well, up to now here, what I'm considering is, as I said, these black holes. Now, if I want to describe these bubbles in this system, I will consider some more complicated black hole whose horizon is, well, rather inhomogeneous, and will describe and encode the physics of these bubbles, right? So now, this will be a little bit technical discussion, but I will not bore you with equations. The idea is that I need some black hole in the bulk whose interior reproduces the metastable phase, so that's kind of the inside of the bubble, and whose exterior extends to infinity and connects to the state that describes the metastable phase, right? So now let's look a little bit more in concrete to these solutions, but the claim is that these solutions should exist if these critical bubbles that connect these two regions can be described holographically. So, okay, remarks about the solution. Remember, this is kind of the object I'm trying to construct. Well, they have spherical symmetry along the boundary, radial direction in the boundary, right? So again, if you think of your field theory living at the boundary, this should be spherically symmetric like the bubbles along these directions. But then, because this is a black hole solution in the bulk, it should also depend on the holographic direction, which in this diagram is kind of the vertical axis. And this is a static configuration. So remember, the critical bubble is the one that doesn't move. It's unstable, but as long as you don't touch it, it doesn't move. So this means what I need is to find, well, some solution that depends on two coordinates, but not on time. And I have to solve a PDE. Right, so that's what I need. And well, and you have to solve this. So this is Einstein's equations, right? So Einstein's equations are typically a complicated thing to solve, and they also have gauge redundancy, so you should know how to deal with it properly. Well, we discussed that in the paper. Actually, the concrete method we use is the Turk trick. It's kind of reviewed in this nice paper. But with that, you get a well-posed problem that you can solve, right? And okay, if you want to know the details, you can ask me either at the end or later. But okay, it's kind of a thing which is technical and it's well, it's not us that invented it. It's something that people have been playing with during the years. So let's see how we construct this with these symmetries and yeah, solving this numerical equation, right? So again, let's go to our phase diagram. Our intuition tells us, well, I should pause because I gave a lot of information. Is there any question? No, no news, good news, I guess.
Yeah. This de Turk trick, you mentioned it. What is it? I know it's difficult to solve elliptic problems, so just out of interest, how does it work?
Right. So the idea is that if you just specify an ansatz for your equations, with these symmetries, well, because this is gravity, you still have some gauge redundancies. So the equations you get in the end are both second order and first order, and it's not super clear what are the degrees of freedom you want to kill to be able to solve them. So the idea is that naively, what you get is not a well-posed elliptical problem. So with this de Turk trick, what you would do is to consider a reference metric, which kind of fixes the gauge everywhere. That gives you a system of second order equations, which is elliptical and well posed. And in a way, the gauge is fixed dynamically. Yeah, I'm happy to discuss it further if you want. It's actually very nice and there's a lot of mathematics behind. But the thing is that if you do it properly, it works and you're able to find these solutions. And, you know, in rather generic situations, it's a thing that you can use to solve static Einstein's equation.
Thanks. And yeah, otherwise I'm following. So yeah, thanks.
Okay, thank you.
Right there.
Good. Right, so let's construct this solution. And then the intuition we have is that close to this turning point, as it happens when you analyze this in effective theories, you expect that the bubbles are small. So the idea is that if I take one of these black holes that describe a metastable phase and perturb it slightly, well, if I'm lucky enough, or if I have enough patience, it will fall into the new solution. Well, we either had luck or had patience, but it actually does. So you start with that solution and it eventually falls into a new solution whose energy density at the center of the bubble is different from the one you started with, right? So this is not a picture anymore. This is a result from the computation. What you get is, well, this kind of black object in the bulk, which are a small inhomogeneity. And this homogeneity is precisely describing at the boundary your inhomogeneity, if you want, the energy density inhomogeneity of the plasma. Okay. And now, once you have one solution, you won, because it's very easy to start changing the temperature and let this solution relax again into a new solution. So for instance, well, you can start finding different solutions. And as you get closer to TC, you get what you expect, which is that the stable phase is reached and connected through this inhomogeneous horizon to the stable phase outside, right? And then, well, you can kind of scan different temperatures. Well, this is kind of how it looks like from closer, and describes this critical bubble. And if you scan all the range, which is relevant to us between T0, and TC, indeed, you find, well, this kind of energy density profile at the origin of the bubble, and then the different profiles connected, right? So now we are going to analyze the different physical properties of these bubbles very briefly. But for example, and as I said, holography gives you a very precise way to compute the properties of energy momentum tensor and other quantities. So here I'm plotting the profile of the energy density, well, normalized to the energy density at infinity and in the low phase. So as I was saying, close to the churning point, the profile does not explore very much all the energy range. But as you go closer to TC, well, this kind of characteristic hyperbolic tangent profile develops, and then you connect the metastable with the stable phase. And now you see this very clearly, right? So when you are close to the churning point, well, the profile is more or less Gaussian with a characteristic scale. Sorry, this is not the surface tension. I should have used a different letter there. But also the hyperbolic tangent, just because you have two parameters, you can also adjust it so that it coincides more or less. And then as you depart from the spinodal point, well, you see that the Gaussian stops being a good approximation, but the hyperbolic tangent is still good. Okay. Good. So actually you can kind of estimate, by fitting your profiles to a hyperbolic tangent of this sort, you can plot the radius of the bubble as a function of the temperature, and also the thickness of the wall, which is measured by this parameter, as a function of the temperature. And here you see something that you already expected in a way, which is that while the radius of the bubble diverges when you go closer to the critical temperature, which corresponds to 1 in this plot, the thickness of the wall saturates. So that's kind of manifestation that what we were discussing when we were talking about this thin wall approximation will apply. And then, okay, it's kind of interesting to see that the characteristic size of the bubble also diverges when you go close to the spinodal point. In a way, that's because, well, you have these two quantities diverging and combining so that the Gaussian is, it's a good approximation. I think people refer to this sometimes as the fat wall approximation, but okay, let's leave it there. Now we saw the pressure profile. We can also look at the pressures. We saw the energy, sorry, we can look at the pressure. So, okay, this is kind of the pressure and final temperature for the homogeneous configurations. So you see where they cross, it's where the phase transition happens. And then here we have two pressures, the transverse pressure to the radial direction in the gauge theory side, sorry, which is kind of perpendicular to it, and the longitudinal, right? And something we checked in our numerics that the conservation of the energy momentum tensor is satisfied. So this equation, which is the only one which is non-trivial with the symmetries we are assuming, well, it actually has to be satisfied because it's a consequence of the equations in the bulk, but in a way it gives you a check for your numerics. Good, and then you see the properties like the longitudinal pressure decreases monotonically, while the transverse pressure, well, has this kind of bump. And yeah, when you approach TC, the longitudinal kind of becomes constant. And that's because you develop the wall. Well, and then most importantly for our purposes of computing this tunneling rate or the nucleation probability, well, you need to access as we discussed at the beginning, the free energy, and you do that by integrating a quantity that you can think of as the free energy density, which you can also read from your solutions. Well, in this quantity, you already see kind of what we were saying about this thin wall approximation, right? So when you are close to TC, you kind of develop this free energy difference between the inside of the bubble and the outside. So, well, here's precisely what we're discussing, no? The total free energy will be given by the difference times the volume of this piece, sorry, and then the contribution of the wall, which is just moving as you change the temperature, and will give you the surface tension. So, cool, with these quantities, we can now integrate this curve to get delta F and see what's the suppression. And that's kind of the main result, I guess, or one of the main results of our paper, which is this, this kind of the curve you normally get in this situation and this kind of problems. But okay, we can make some remarks. One is that when you are close to TC, well, this thin wall approximation applies. So you actually recover what you expect, from our earlier discussion, right? And actually in this limit, well, this gives you a way to compute the surface tension. So, well, and then it diverges like T minus Tc to the minus 2. Well, the surface tension in our case, well, it's just a number you get from your numerics. And note that it is not connected to neither the characteristic, natural units to which you would compare it is the source, this deformation that you are doing to your theory that introduces this operator. So that's the only, dimensionful parameter I'm introducing in the theory. And you see that sigma, it's not related. So it's kind of 10 to the minus 3, this quantity. Or the other maybe natural to quantity to compare it to is the critical temperature. Well, and then in this case, we get kind of order 1 suppression. In the opposite limit, well, we get this, here we just fit to our numerics, and then we get that this goes like T minus T naught to the 0.76. Well, if you want, this is compatible with 3/4. And this is not the usual 3/2 that people discuss from this early paper. Well, we believe that this is just model dependent, depending on what kind of potential you have. The way you approach to this annihilation of the maximum with the minimum will change, and that will give you a different potential. And in our case, a different power. And in our case, it gives you this number. But yeah, we think this is not universal. Good. But okay, now kind of we have this technique and this tool. The natural thing to do is to ask, would this agree with any effective approach? Okay, I'm saying effective, probably broadly understood, approach to this same problem. So what I will discuss next is 2 different ways in which you could build an effective action that are kind of sensible enough so that you expect them to reproduce the same physics, and see what we get. Well, so that's kind of the part of assessment of the effective approach. Before I change gears, maybe it's a natural moment to make a 10-second pause, and maybe someone wants to ask anything.
I have a question.
Yes.
So you have a final result here for this nucleation probability, or this delta F. And it depended, I guess, on the form of the theory that you started with, this 5D theory, which had a potential in it. How much freedom is there in that setup?
Right. So you have a lot of freedom. Yeah, maybe I didn't stress this because it's kind of always in the back of my mind. So we are not attempting with this program, if you want, at least for now, to get quantitative results that you could plug and say, okay, my expected gravitational wave is this, and this is something that we will observe, right? So really here is like being able to construct or to get these quantities in a controlled manner from microscopics, and then being able to assess different assumptions maybe that are made when one is just assuming some effective theory and maybe does not have access to this microscopic, right? Or put differently, is there anything universal we can say from the microscopic theory? So, okay, kind of the analogy that also David likes is that this is pretty much what people was discussing when you were using holography in heavy ions, right? So in heavy ions, what people would use typically is hydrodynamics. But then when the system is out of hydrodynamics, you don't have any access. Well, have some access, but holographic will tell you, how you approach this hydrodynamic regime and when hydrodynamics breaks down or not. So I guess our approach to this is right now not constructing anything, measurable or quantitative. It's more about checking the effective approach. I mean, hydrodynamics in the end is also an effective approach. So now answering your question, we have a lot of freedom, so you could change that potential. And then you would get, changes in the phase transition. And maybe that's one of the things maybe in the end I wanted to comment, but I say it now. You can see which of these properties we see here are sensitive to changing those parameters, right? If you were more a string theory person, you would say, maybe the potential is very much constrained by string theory, so you could also look at those models that are top-down. So that would be another thing, right? Like say, if I take a truly string theory model, what is the answer I get? Yeah, I don't know if this is, I give you a
Yeah.
satisfactory answer.
I guess it's also possible that with this setup, with this pipeline, with this approach, this holographic approach, the class of models that you have access to is in principle different to the class of models that we normally have access to perturbatively. So it could be that I don't know, the results in general are in a different part of space, that the properties of the transitions are in general different potentially for the class of strongly coupled models than the class of weakly coupled models.
That's a valid thing, but I think that's something you could also precisely assess, right? So in holography gives you access to large N strongly coupled models. So I think well, that's always the case, I suspect, at least right now, unless you start considering quantum correction, but that's complicated. Yeah. So, but
Yeah.
I think there are some overlaps that you could consider. No? Like, I mean, you could also consider large N perturbatively. So that's something you could assess and then see, okay, this thing it happened the same hydrodynamics, right? So if you study hydrodynamics at weak coupling, you get some prediction for transport coefficients, and at large coupling, you get this 1/4 pi for the shear, right? So I mean, I think these are precisely the kind of questions you can ask. What things are dependent on the coupling? Yeah,
Thanks.
good. So okay, let me see. I guess I'm doing good with time. Well, if you want to construct such an effective approach, one thing you could, well, this kind of the object I want to consider. So can I construct an action that reproduces the same physics with these properties? Well, famously, this is kind of too naive. You would also consider a kinetic term in front of your scalar. And note that here I'm already ignoring the time derivative. Well, because these bubbles, as I said, are static configurations of the fields. So, okay, the two objects I need to construct is this effective potential and the kinetic term. And as I said, it is natural to identify the field here with the expectation value of the operator I introduce in the value. As much as in the electroweak theory, we consider the vacuum expectation value of the Higgs. Now, something very naive that I'm kind of naming phenomenological construction is to assume that your potential is given by a degree 4 polynomial and then use the equilibrium states that don't know about these bubbles. Sorry for the typo. To construct this polynomial, right? So you constrain your polynomial. Okay, these are kind of the equations, but what I'm asking is that you fix the value on the position of one minimum, you fix the value on the position of the other minimum, and you fix the height of the potential. And in this way, you get a potential which resembles, well, yeah, I'm not actually, sorry. Here I'm comparing two potentials. I said I would construct this in two different ways, and here I'm just saying that the two ways actually give you the same, but okay, this is kind of very bad pedagogically because I didn't introduce the other one. So maybe you can just keep also in your minds that the two approaches that I will say will give you the same approximately potential. But okay. More importantly and more difficult is how to get this kinetic term. So it turns out that if you get a rather constant kinetic term, it gives you a good approximation. So, well, let's see how this goes. I can actually construct the bubbles having the effective action and then tuning my Z, which, yeah, here I'm assuming it depends on T, to match the bubbles I get from holography. So here you have to think of these plots as the plot that you obtain when you get the V polynomial that I just discussed, and you fix Z so that the fit is the best. So they kind of fix, you match the two sizes. And then you see if you do this, so you take this 4 of the polynomial and a constant Z of this order in units of the temperature, then you get a good agreement, right? And then remarkably, this Z, well, again, it's not set by the scale of the temperature. actually you can relate it to the surface tension. So famously, if Z is constant, you can factor it out from your expressions. So you get an expression like this that relates sigma, Z, and your effective potential. And if your effective potential is a polynomial of degree 4, you get this very simple expression in which you have your surface tension, your Z, the difference between the two vacuum expectation values at the critical temperature, and the height, well, the square root of the height of your potential, right? So in a way, well, if you buy that, and at least it is the case in our model, that Z equals to constant is a good approximation, well, you can actually, if you have access to the string, the surface tension, that is something that you compute at TC, you can kind of give an estimate for your Z, which again, if you compare it to the naive estimate that you would get, well, it gives you a good approximation. So here what I'm plotting is the nucleation rate as a function of temperature when you use a set of this order, which is set by the surface tension, compared to the set that you would naively fix out of dimensional analysis. Either if you choose lambda, then you get a factor 10 to the 3 difference, order 3 orders of magnitude of difference, or order t, then you get 1 order of magnitude. Right, so maybe one thing you get from this holographic approach is a way to get this sigma, and if you want this prediction that Z is small, and then it's kind of what you can ask. Okay, how general is it the fact that I can set Z to a constant through the phase transition? Yeah, so that's kind of an open. We checked it in a model, but now I guess it's a game of exploring the parameters of the model and see if this still holds or not. But okay, maybe something to remark is that dimensional analysis here would fail to give you a nucleation probability. And then more complicated, and I guess I have 10 minutes, right? How am I doing with time?
Yeah, you still have 10 minutes roughly, so
Okay. Yeah. Right, so you can actually ask, and this is something we didn't start it in this paper, so it's something that's been already around for, I guess, 5 years now. You could ask, can I construct this effective action directly from holography? So here you try to follow the usual procedure that you do, well, that was done in the past, right? So you would start with your generating functional, which remember, it's constructed by introducing an external source to your path integral, taking the logarithm. And this gives you the vacuum expectation value when you do variations with respect to the source, which in general depends on position. And from this, you can consider the quantum effective action that you would actually eventually identify or use to construct this effective action, which similarly gives you, well, it's kind of the Legendre transform, and gives you the source when you do variation with respect to the VEF. So now, if you consider this on homogeneous solution, well, this equation in a way it's just a differential equations that you can integrate. So if you know J as a function of phi, you can integrate, and precisely because now you are using homogeneous solutions, this part is not here. So naively at least, and well, this is probably correct, but I have to admit there's some confusion in us about this, but okay, let's bear with me. You would identify your effective potential with the integral of the source with respect to the vector. So that's one piece of information. Now the other question is, how can I construct this kinetic term? Well, as I said, you would consider your VEF as a function of the source. You invert this relation and you can integrate it to get the potential that, of course, reproduces the same, well, cases of minima and maxima that we had and we wanted. Good. So now the question is, how can I construct this kinetic term? And the claim is that you can approximate it by looking at the pole of the green function and the residue. Okay, how does this go? Well, if you analyze this expression and start, well, kind of doing small field expansions of this expression, eventually you get that the equations of motion close to a homogeneous state look like this. So your green function evaluated on the difference is equal to 0. Now, if you compare this expression to the equations of motion that you get from this action, well, naturally you would identify whether the zeros of this object, and because this is the inverse of the green function, means the poles of the green function, should be identified with the zeros of this object. Now, this is something that you don't expect to hold generically. And then where this approximation fails, well, it's not completely understood, at least for me, but the idea is that if the homogeneity is too far, well, too big, maybe this is not applicable anymore. But should work when this is small and also when the gradients are small. Because remember here we are also cutting, in a way you are also doing a small gradient expansion when you write this action. So, okay, whenever the gradients are small and the inhomogeneity is small, you expect this to be true. When that's not the case, maybe there are other poles in the green function that would alter this approximation. But okay, nevertheless, this is the best we can do, I think. So the idea is that we have to compute this green function in holography. So for that, well, that's also a prescription. You would introduce an inhomogeneous small source in your background solutions. From it, you would compute the 2-point function, which is, well, the derivative of the VEF with respect to this inhomogeneous source, and then set the source to 0. And from here, you would compute the pole of this green function, which I'm denoting by P naught, and the residue, which is R naught. Now, here you already see why this is problematic and why it doesn't always work. Well, a way to see this is that this V effective has some renormalization scheme dependence, while you don't expect the residue and the pole to be scheme dependent. So here you already see that, well, this should fail in some limit. And you can actually make this explicit because we have computed the effective potential independently. So we can check the second derivative obtained from this expression. Well, we can see how close it is to the second derivative of this effective potential we constructed here. And then you see that they actually coincide close to the turning points where you expect this approximation to hold, because it's the case where the pole is close to the origin and the gradient expansion is valid. And then, well, it gives you kind of a factor of 2 error here, and then it fails miserably in this region, but in this region we are not interested because it's not where the phase transition happens. So okay, if you bear with me, and I think I have to admit that we don't really know how to compute this Z fully, but if you agree that this is a good approximation, at least I see this factor 2, we can actually, well, get this Z, and then with V and Z, I can again find the bubbles from this effective action and compare them to the holographic result. And again, this is what I get, right? So what I get is when the homogeneity is small, they kind of agree, as I expected. When the deviation from the homogeneous solution is the largest, then is when it gives me more error, as you can see here, but okay, it's not super bad. And then eventually it's again good because it's matching to homogeneous solution. So kind of the deviation is in the middle, but it's a small region. So, okay. In a way, it's kind of failing to compute precisely the thickness of the wall, but it gives me correctly the size of the bubble. Okay, so I think that even though all these approximations and these things that we don't completely understand, still the approximation is pretty good. And this is something also you can now ask, okay, how much this depended on the model and can we do better? Well, that's kind of, I guess, a work in progress. But then again, from this you can show that the nucleation rate from the two approaches agree pretty well. Good. So with this, I will conclude. Well, maybe there's some question about this part, I don't know. Otherwise, I will conclude. Okay. So, well, we provided a microscopic description of these critical bubbles in terms of the inhomogeneous black hole geometries. which look like this and connect the bulk geometry with the boundary. This allows for an assessment of the effective approach, and then, well, you can ask, depending how you construct this, whether it's better or worse, and what things are universal. I guess that we can conclude that so far these effective actions we constructed reproduce the results nicely, even though there are some subtleties. And maybe another take-home message is that this surface tension play a crucial role in determining the kinetic term, especially in the cases where you can assume it's a constant. So there's also a kind of a nice thing that it's worth exploring how robust it is, comparing it to other models, and yeah. And then maybe, well, there's many things you could do now that you can. So far, what I explained is, well, it's kind of familiar to you. This kind of bubbles we constructed are these O3 configurations, but now you can ask whether you can find the O4 configuration, in which, well, you have time dependent. So this, I don't really have a good intuition how this would look like holographically, because, well, if you go to the Lorentzian signature of this, should be something that is expanding in time, and okay, maybe most remarkably, there's something in between that is inhomogeneous in time. So okay, at least I don't know how much you will learn, but I think it's also a nice question to ask that I plan to do it in the future. Yeah, how to construct this and whether you can learn something or not. And then, okay, applications to QCD and neutron stars. There are tons of QCD models in holography. So now you could analyze bubble nucleation in that scenario. There's another question that, okay, maybe some of you know very well. So when you compute this nucleation rate, well, there's kind of two important characters. One is this suppression, exponential suppression, which is the one I was discussing today. But then you also have the fluctuation determinant. So, well, the idea is that we expect this to be connected to fluctuations of the bubble itself. So it's an interesting question of whether we can construct and study these fluctuations of the geometry and relate them to this determinant and see whether, well, maybe this determinant may overcome at some point this exponential suppression. Again, from a microscopic computation. And then, okay, there are many more things, like try to see whether some objects can act as nucleation sites for this for this bubble nucleation. Maybe finite volume effects and many more things that I don't have the time to discuss, but I'm happy to elaborate a little bit more. But okay, I think it's good timing to leave it here. Thank you for the attention.
Thank you very much, Javier. This was really interesting. So, do we have any question in the Zoom? Maybe I do have one. You mentioned in the beginning that, yeah, there's this transition line in the QCD phase diagram that is expected to exist. But from what I understand, it's still under debate whether, like, there's no definite proof of having this first order phase transition line. Could you say anything about that with these holographic methods? Like, could you have a better argument to show that it truly exists or not?
Well, so I think when you try to study that phase diagram using holography, it's really a bit like model building. So you don't really have first principles to assess whether in QCD there's a critical line. But I guess my take there is that holography provides you a way to model this phase diagram. And given that it's a very complicated problem for which there are many models and many, more or less justified, I would take holography as another one of those. So if that's the case, well, the models I'm aware of, they all have this phase transition in holography. And then who knows, maybe when some of these detections, I mean, gravitational waves are not the only ones that give you access to this kind of structure of neutron stars. But when these measurements get more and more precise, well, it could happen that the holographic models are the ones that give you the best fit to the observations. We don't know, but I guess my answer is that, well, most of the holographic models, if not all of them, do have this phase transition. And then it's up to the experiments to determine at this point, I think, which is the best model.
Okay, thanks. So any other question?
Maybe I have a question for the audience.
Yeah,
So
go ahead.
yeah, this suppression of the surface tension that Javi discussed, the fact that it's small in the natural units that you would expect it to be order one, is something that is also seen in QCD or in pure Young-Mills theories, let's say, because the surface tension can be computed on the lattice. And it turns out to be, again, small compared to dimension analysis estimates. So I was wondering whether anybody has some intuition for why this is the case. Maybe not.
I don't have any intuition. Maybe relatedly, this Z factor is small, right? That you find.
Yes.
What would it mean to be one in like? So I wasn't quite sure of like exactly the normalization of the field.
Right. So, well,
What
if you
small?
have one, it's canonically normalized.
No, I'm aware, but I can always like I can do a field redefinition in my path integral, right? To change phi to phi times some number, and then I have the same kind of form. So at some point, you've picked a normalization of curly phi,
Right.
and like
So
where did that come in?
phi for me is defined as the vacuum expectation value of the operator. So this is
But I could choose that operator to be some number times that operator, and that would change the normalization of phi, right? So I guess how
well,
did
but
you
then
pick
you're
that
changing
operator?
also the source. So yeah, I mean, you can. I mean, it's conservation of misery here also because if you make this number big because you put a 100 in front, then you have to change m.
Okay.
But if you take both, you don't. Yeah.
So is Z small no matter what you do? Is there something that forces Z to be small, or does it somehow relate to a choice that you've made?
I don't think it's related to the choice.
Okay.
I think maybe, Javi, if you go to the equation that shows the relationship between sigma and Z and the free energy and yeah, this one here. So sigma doesn't depend on how you normalize things. It's just
Yeah, it's
what
energy
energy
from the
cost you
barrier.
have at the wall, right?
Yeah.
So you can
Okay.
shift things around on the right-hand side, but the left-hand side is the same. So that's
Z
why,
delta phi. Okay.
yeah,
That's great. Z delta phi. Okay, and sigma is small, is what you're saying. So it's
yeah,
not to do with
Right,
normalization.
right, right.
yeah. And that's very
Okay.
important because if sigma is small, parametrically, then you nucleate the bubbles closer than you would have expected to TC. And that suppresses the gravitational wave production because
Yeah.
that also results in a smaller velocity for the bubbles. So yeah,
This I think is something that people have seen in like SUN lattice
yes,
simulations, right, as well.
actually, yes, yes. So on the lattice, people have computed this for, I think, SUN and maybe even SPN or different non-abelian pure gauge theories that have a first order phase transition. And it happens to be small also in those cases, yeah.
Yeah, it's an interesting result.
Yeah.
Are all of these simulations done in the non-preservative regime, or
I
For
think
us,
yeah,
yes.
they are because of the phase transition. Yeah, yeah, okay.
there's no
Yeah.
scale in the problem to make it.
Yeah. Yeah. So I guess it kind of evades these intuitions that one can get from perturbation theory, where this sigma wouldn't be small. But sort of, yeah.
Yeah. Yeah, although I don't have intuition for why weak coupling should make this bigger or smaller compared to strong coupling. So in a pure Yang-Mills theory, I would have expected that since the only scale is, let's say, lambda QCD, like the confining scale, that the surface tension would be, lambda cubed times a number of order one, not 10 times smaller or, 100 times smaller. In fact, I think in SUN, it's 100 times smaller in, real SUN on the lattice. Yeah.
Intriguing.
Okay, well, we're a bit over time, so maybe it's a good time to stop. So let's thank our speaker again.